It is my great pleasure and honor to introduce Mike Goodchild. This is the most easiest and difficult task to do. And I don't think there's any introduction needed, but as many of us know, Mike has been so successful at doing what he likes to do. But so far I'm aware of one thing he has not succeeded, that's his retirement. That has to do a little bit with this project, but this year one factor we considered where to host this meeting is to help Mike maybe minimize his travel a little bit and help him achieve his retirement goals faster. Without further ado, Mike.
Thank you, Xiaowen. I should first apologize for this and just simply say you should see the other guy. And I thought what I'd like to do is to basically follow on from the question I just asked, which is what should we be thinking about at the end of year 3 and the beginning of year 4 of a 5-year project? Knowing that any kind of continuation, whether it's new grants, whether it's bifurcation into many new grants, all of that will have to begin very soon. If there's a 2-year time remaining, we will need that time to think about where we're going. So I wanted to visit the vision of CyberGIS. This is not a time, I think, to reiterate the original vision. It's a time, I think, to enhance and update the vision. And so that's what I'd like to do in the next few minutes. This may not take the entire time available, which would be great because then we could open things up for discussion. But what I'm hoping to do is put some thoughts in your heads that will help us get through the next 2.5 days and put us in a position to think about, begin at least thinking about where we're going next. So we're 3 years in, and so here are the sorts of questions I think we ought to be asking at this point. How has our vision changed since the proposal was written? And the proposal, of course, was written more than 3 years ago, and this is a very fast-moving field, so it would be very surprising if our vision had not changed. And even our definition of CyberGIS may have changed. So the kinds of questions I want to start people thinking about are what will be the next phase and how will it be different from what we've been doing, both in terms of infrastructure but also in terms of vision and agenda. Then secondly, are we measuring success appropriately? And I think that's an issue that we've kept coming back to at various points during the project and is worth revisiting now because I think our metrics of success need to be different in year 4 than they were in year 1. So I want to talk about 5 different areas, and in each of these areas I suggest there is room for rethinking the vision of CyberGIS. The first is the set of problems we're here to tackle. What is CyberGIS trying to do? What problems is it trying to solve? And I want to talk about that because I think that's something that certainly my thinking has advanced quite substantially over the last 3 years. Secondly, analysis and modeling, which is, of course, key thrust of the whole project. Third, broadening the base of users. So who exactly do we today think about as the users of CyberGIS? Who should we be thinking about 2 years from now as the users of CyberGIS? And I think that's a very important question that we need to get our heads around. Fourth, the science of CyberGIS. And notice I say the science of CyberGIS and not science with CyberGIS. And I think that's a very important distinction, and I want to suggest some ways in which we ought to be thinking about the science of CyberGIS. And that has a lot to do with the longevity of this field. Unless we can be clear about what the science of CyberGIS is, we're going to have trouble refunding and continuing this effort. And then the last one is education, and I apologize for putting education last. Somehow it always ends up last on the list. It really ought to be first, but logically I think that's where it belongs in this sequence. So those are the 5 areas I want to talk about for the next little while. So what's the story so far? What have we achieved in writing the proposal, putting the team together, and 3 years in? And here's my definition of CyberGIS. Is not quite the same as you've heard, but I think the simplest way to think about CyberGIS is as a subset of cyber infrastructure. Cyber infrastructure as defined by Dan Atkins and as further developed by NSF and the Office of Cyber Infrastructure. And then it is the subset which is specific to geospatial activities. And I think that probably satisfies most of our requirements for definition. So what are the components of CyberGIS? They are, of course, the components of cyber infrastructure. And so we have, here are three: high-performance computing, as applied specifically to geospatial analysis and modeling, primarily motivated by the observation that such problems are often compute intensive. So a lot of the discussion in the proposal and the discussion over the past 3 years has been about how geospatial problems often require high-performance computing. And that's been, I think, a major motivation for what we've done. Secondly, cyber infrastructure is about distributed and collaborative systems, and within those systems, using geospatial data and tools, and inevitably, because of the nature of geospatial data, strong emphasis on visualization. And then third, community building. Of course, that's a lot of what we're doing in this project and will be discussed at length during this meeting. Okay, so on the question of large problems, clearly there is no shortage of large problems in this field. Okay, and here's just 3 examples. If you took a global digital elevation model at 30-meter resolution, fairly coarse, you would have approximately 5 times 10 to the 11th data elements. So you're already at terascale. And if you wanted to solve a problem like intervisibility, that would be an enormously compute-intensive problem for which you would undoubtedly need high-performance computing. And not surprisingly, that's one of the examples that we've used in trying to illustrate CyberGIS. Second, let's look at longitudinal change in land cover. And let's make it fairly coarse. Let's say a 1 hectare resolution, which is fairly coarse. We don't need to push it all the way down to 1 meter. That would give us 5 times 10 to the 10th data elements per time slice. So we're already at terascale. And if we thought through the whole history of Landsat, 20 visits per year for the last 40 years, we would be at 4 times 10 to the 13th, so we'd be approaching petascale. So as you can see, we have no problem constructing large problems, and in that second case, that's been a problem that potentially has been around now for 40 years. And a quick third example, suppose we took the entire US vehicle fleet and fixed its location of every vehicle every second. Now we're talking petascale and probably exascale. So it's not a problem at all to construct examples which are compute intensive on the one hand and also data intensive on the other. So how do we measure success in this world? I've always emphasized, and I don't want to beat a dead horse here, but I think our ultimate measure of success is this: what new scientific discoveries could not have been made without CyberGIS? And that's a question we've struggled with over and over and over again. It's a difficult question, and I don't think yet we have a clear, compelling example of a scientific advance made with CyberGIS that could not have been made without it. And that ultimately, I'd suggest, certainly from an NSF perspective, is the measure of success. But we can introduce other ones because these days in the world of big data, it's not just about scientific discovery. So we could also suggest this: what new problems could not have been solved without CyberGIS? Or what new decisions could not have been made without CyberGIS? Right? Or what new predictions, in context of big data, could not have been made without CyberGIS? Okay? So all of these, I think, are strongly related, and they all, I'd suggest, are the primary measures of success. And we will need, I think, to have some clarity in the answer to these questions over the next 2 years. Okay? So just to put this in historic perspective, all of these are of the form, what could not have been done without X? And if you substitute X equals GIS and put this back to approximately 1990, these are the questions that were being asked about GIS in 1990, and which we, I'm speaking for NCGIA, myself, but many other people, we had to answer. find me examples of problems or scientific discoveries that could not have been made without GIS. And we struggled with that for a long time. And I think, ultimately, we addressed the question. So I think, again, let me suggest that this is a primary objective for us over the next couple of years. Now, in approaching big problems, and I deliberately chose the example of Landsat because it goes back 40 years, in approaching large problems, our strategy as GIS scientists has always been essentially divide and conquer. Divide and conquer has been the strategy for tackling large spatial problems. And also large temporal problems, if you like, or large spatio-temporal problems, because the time slices become the divide and conquer. You study one slice at a time, or you study one area at a time. Right? And this is basically based on the principle that familiar geospatial analyses can be partitioned geographically. So most people, when they need to do an intervisibility analysis, don't do it for the entire surface of the globe. They might do it for a 1 degree square. And going back to my example of a 30-meter DEM, that would be 10 to the 7th data elements at the equator, and that would be something manageable in conventional computing. Similarly, when we study longitudinal change in land cover, typically what we do is classify one Landsat scene at a time. We divide and conquer the world into Landsat scenes, and that takes us down to about 10 to the 7th data elements again. Right? Manageable with conventional computing. So divide and conquer then has always given us the ability to handle these problems which, if you aggregate them all together, are huge. But by divide and conquer allows them to be manageable. What you miss, of course, in divide and conquer is the interactions between the pieces. Right? So when you classify land cover over one Landsat scene, you ignore what's happening off the edge of the scene. When you solve the intervisibility problem on a 1 degree square, you mess up the edge of the square because you can't see beyond it. Right? So divide and conquer always has a cost. And there are various techniques for getting over this, which we've studied over the years. Or my subset of my vehicle example, tracking a subset of vehicles in one metropolitan area would reduce this to 10 to the 7th data elements per second. Still enormous if you run it longitudinally, but becoming manageable. And this is the strategy that we have always used. Right? So a very important question here then is, from the significance of CyberGIS, to answer my question, what can't be solved without CyberGIS? The answer is problems that can't be solved by divide and conquer, or problems for which the cost of solving with divide and conquer is excessive. Right? So over what set of problems does divide and conquer not work? And is that, in asking that question, are we dealing with the complete set of problems? And I think that's a very important way of thinking about this. So here's the first elements of an enhanced vision. Okay. In the set of geospatial problems, only some are amenable to divide and conquer. The ones which are not are the candidates for compelling examples of CyberGIS producing advances. Because of our reliance on divide and conquer, we do not give such problems serious consideration. We don't even see such problems. We're not even able to enumerate them. Right? They're so far below our consciousness we don't even think about them. So my suggestion is there is a set of problems out there, but they're not problems that we normally recognize. And until we do, we're not going to come up with examples of compelling applications of CyberGIS. So here's the agenda, right? Think about what the complete set of problems is and which ones don't make themselves amenable to divide and conquer. So CyberGIS invites us to rethink our problem set. We're not going to make a case for CyberGIS by considering old problems. We have to rethink the problem set. CyberGIS will be measured not by the existing problems it solves, but by the new problems that it makes solvable. And that's a very different perspective, I think, from one we've taken over the past 3 years. So that's the first segment, and that's really about the data volume problem, the big problem, and how CyberGIS can address them. So why is divide and conquer acceptable? And why do we rely on it so frequently? And this is trying to get at this question then of what kinds of problems are not amenable to divide and conquer. First, because most social interactions occur over short distances. So by dividing the world, you still preserve most social interactions. And this is something that geographers have recognized for a long time as distance decay. And it's allowed us to get away with analyzing the world one segment at a time, one piece at a time. Long-distance interactions in this world are problematic, right? Because they create relationships between the pieces of a divide and conquered world. But they're increasingly common in a virtual world. So as we move into the virtual world, we are going to have to deal more and more with long-distance social interactions, and that makes it more and more difficult to study social problems by divide and conquer. We often think about the world as partitioned into places, which is very convenient because it allows us to study the world one place at a time. So in thinking of cities as discrete objects, we have partitioned the world into manageable pieces. But as soon as we start thinking of population density as a field, as a continuum, things are much less amenable to divide and conquer. And then lastly, physical interactions. Many physical interactions occur over short distances, and so divide and conquer is fine. But there are many kinds of physical interactions, and we're now starting to realize the kinds of teleconnections which exist within the Earth system. Those teleconnections are problematic for divide and conquer. They're relationships between distant places which cannot be handled in a world in which we segment into subsets. So just a few illustrations. I love this front cover from the New Yorker from 2001, just after, in fact, quite shortly after 9/11. It bears looking at. There's a lovely, this area up here, the unmitigated goals. I think that was pretty. And down here, forget about it, Stan. There's some lovely little pieces in here. But what it's illustrating, of course, is that you can study society in New York by partitioning, by divide and conquer, and studying it one segment at a time. And that's what makes the problem manageable. By contrast, here's the famous Facebook example of long-distance connections in the social interaction, and making the point then that you can only study social interactions in the Facebook world by studying the entire globe. You can't divide and conquer. This one's kind of, I wondered whether we're suffering here from the use of a Platte Carré projection, because the number of connections across the Pacific is remarkably low. And is this simply because we've interrupted the world at 180 for the dateline? I don't know. And this one, I Googled butterfly effect, and I came up with this, which is a really nice. Butterfly effect, of course, being the classic example where a very small disturbance in the atmosphere on one side of the Earth eventually propagates into a massive disturbance on the other side of the Earth. The classic example of teleconnection, right? And there are some lovely examples in here of how 9/11 pissed off the Saudi high rollers, boosted Al-Qaeda enrollment, and got us all to put eggplant on our pizza. And if you look through here, we have the tanking of the stock market caused layoffs on Wall Street, which caused sushi joints to close, which caused the yellowtail tuna population to explode, which decimated the anchovy population, so that a piece of a slice of pizza with white anchovies skyrocketed. And as a result, people switched to eggplant on their pizza, which boosted the price of eggplant worldwide and boosted the price of baba ganoush. And as a result, there was crisis in the Middle East. Those sorts of connections, right, are what I'm really getting at. Okay, so let's move to the second area, which is analysis and modeling. And here, our approach in this project has been to integrate functionality, to think of CyberGIS as integrated functionality serving an interoperable data environment. How do we measure success in that area? How successful have we been? And what should our vision be for follow-on activities? So this is all about interoperable data, and data become interoperable when you make them self-descriptive. So think, for example, of how TIFF is extended to GeoTIFF. So at the front end of a GeoTIFF file, you have the necessary information to integrate that with other geographic data because you have the parameters of the projection and so on. And so in this interoperable world, essentially it amounts to hiding details of implementation, hiding projections and datums, hiding alternative field representations so the user doesn't have to engage with them, thus simplifying the user interface. And the underlying principle, of course, is that the user should engage only with those details that affect the science, uncertainty being one, a major issue for any kind of scientific investigation. So where are we now? And I'd suggest we are still largely in a world of fragmented, balkanized tools. It is extremely difficult to plug and play with analytic tools in a spatial world. And users must engage with myriad details in their analysis, leading to a steep learning curve. We force users to engage with details such as map projections, datums, the precise formats of our data. We force users to engage with pixels instead of with complete assemblages of pixels. Our models generally are not interoperable. It's very difficult to think of models in terms of plug and play. There's no common language, no common data format for modeling. So even though it's easy to identify at least 200 models of any scientific domain, they're essentially not interoperable. It's very difficult to substitute one model for another. We're a long, long way from this ideal world of plug-and-play modeling. And this is true, unfortunately, even in the limited domain of geospatial analysis and modeling. We narrow the world by thinking only of the geospatial or space-time world, but even that doesn't resolve this problem. And here's the thing that I find most troubling, which is that every effort to integrate spatial analysis and modeling. Let's go back to the innovation which was R. When R came in, I'm sure part of its vision was to integrate spatial analysis and modeling. But what happens inevitably, human nature being what it is that integration effort becomes just another case. Every effort at coordination becomes just another project to coordinate. How do we get out of this? How do we avoid this endless cycle of innovation becoming yet another dimension of complexity? I don't know the answer, but I think this is something we need to be thinking about. So, elements of a vision, part 2. Our vision is an environment for analysis and modeling backed by powerful distributed computation, yes. But hiding as many implementation details as possible. Meaning then a new generation of the GIS user interface, allowing the user interface to focus on science rather than details which the user should not have to be concerned with. And ultimately here, I think what we're talking about is the original but much neglected goal of GIS. This was essentially about integrating knowledge in a framework of space and time. But it's actually something on which we have, I'd suggest, made remarkably little progress. And part of our problem is that we still see GIS as about maps. And maps are great at integrating horizontally, but maps don't do much for integrating vertically. We can talk at length about many of these issues, but I just wanted to raise them as flags for the next couple of days. Okay, third topic is broadening the base. And here we have to ask the question, who are the users of CyberGIS? In our vision, as we develop CyberGIS, who are the users going to be? And I'd suggest 4 models. Number 1, the users of CyberGIS will be a subset of the GIS community, a subset of people who are already experts in GIS. That's a very limiting vision, because it limits us to just a subset of the people we already interact with. Alternatively, we could say that our vision for the user base is the next generation of GIS experts. In other words, in the future, to be a GIS expert, you must be a CyberGIS expert. That's taking the entire GIS community and redefining it as being CyberGIS aware. Or a third is that CyberGIS is not about the existing GIS community, it's about expanding that community. It's about the next, fill in the number, 5 million if you like, the next 5 million users of GIS will be people who interact with CyberGIS, not traditional GIS. That's, I'd suggest, a much more ambitious, much more challenging model, but one that we ought to be thinking about seriously. And the fourth, the Broadened base simply consists of everybody, the average citizen. That's obviously very challenging, but I'd suggest of these, I would think number 3 is the one we should really focus on as a group. So what does this mean? Well, number 1 clearly means business as usual. It means an interface which is accessible only to a small set of experts. It means a group becoming engaged with CyberGIS because they are technologically adventurous. Their motivation is to grab the latest technology. And that's very different from saying their motivation is because they have a genuine problem to solve. I'd suggest number 1 is not going to be the group who has a genuine problem to solve. It's the group who like new technology. It's not until you get down to number 2 or number 3 that you really satisfy that idea of a user community who have genuine problems to solve. And of course that takes us outside the GIS community, and I think it should take us outside the GIS community. So, elements of a vision, part 3. CyberGIS is a technology that is adopted because the benefits of doing so outweigh the costs of learning how. Again, a very difficult criterion to meet. It doesn't rely on people being motivated to be technologically advanced. It relies on people being motivated because they have a problem to solve and they can see that this solution is easier than the alternative. It puts a very stringent requirement on the user interface to CyberGIS. So a technology then that reaches beyond what we think of as the GIS community. And perhaps even a technology that has something to offer to the average citizen. I don't think that's entirely beyond the bounds of possibility. So number 4 is the science of CyberGIS, and I mentioned before that I'm talking here about the science of CyberGIS, not science with CyberGIS. And so here I'm thinking about the principles of CyberGIS. And let's go back to GIS Science and ask, what are the principles of GIS Science? And of course, Luke has long favored the idea that 2 of the profound principles are spatial dependence and spatial heterogeneity. Extend that to space and time. I think we need to these days. And then we can get into some more less obvious, more perhaps nuanced principles. One that I'm greatly in favor of is this: relative accuracy is always better than absolute accuracy. A very useful principle, I think, for GIS. And a polyline representation of a curve is always shorter than the curve. I can enumerate many of these, but my point is simply that in GIS Science we have a set of principles. Some of them very profound, some of them, perhaps you could argue, fairly superficial. So, what additional principles arise when we move into the world of CyberGIS? Is there a CyberGIS Science that's an extension of GIS Science? And what are its principles? And let me suggest, I haven't really thought this through, but here's a suggestion of one direction we might go in, which is this: any geographical system can be modeled as a set of semi-independent parallel systems. Of course, it puts a lot of emphasis on the word semi. What exactly does semi mean? But it does deal with this issue of divide and conquer, which I've suggested is a key issue in deciding what exactly CyberGIS is about. So what does it mean to partition the geographical system into a set of semi-independent parallel systems? Should the partitioning be static or dynamic? As we move through time, should the partitioning of a system be fixed or should it be dynamic? Can there be a hierarchy of partitions? Can the system be partitioned at different levels, each level being appropriate for the solution of some kind of problem? The answer, of course, is yes, but these are the kinds of things I think we need to think through. Can there be multiple overlapping partitions? So is the partitioning that you need for the solution of social problems different from the partitioning you need for environmental problems, and what are the consequences of that? Is partitioning the best approach? Should we be thinking about fuzzy partitions? Should we be thinking about not partitioning, but by addressing a problem by proximity to archetypes, proximity to nodes? Okay. So elements of a vision, part 4. I think we need to be thinking about a science of CyberGIS with a set of distinct principles. Those principles then provide the foundation for teaching about CyberGIS. They're principles which we can expect still to be true in 20 years, independent of today's technology. They're what we might end up calling CyberGIS Science. And that, and I'd suggest only that, is the way in which CyberGIS will achieve a place in the academy. It's only by having its own principles that CyberGIS will gain sufficient respect to have a place in the academy. And if you think back to 1990 and GIS, at that time we were dealing with lots and lots of comments along the lines of GIS is just a tool. CyberGIS is just a tool in 2013. GIS is non-intellectual expertise. 2013, CyberGIS is non-intellectual expertise. These are things that we're going to have to address, I suggest. So the last is education, and here my primary concern, I think the thing we need to be most conscious of, is that the field of GIS is advancing very rapidly. What place does it deserve in the curriculum? To what extent should there be a curriculum, a body of knowledge of CyberGIS? Is it, on the other hand, just a flash in the technological pan, or is it truly a new addition to scientific knowledge? And how should we prepare students for a world of CyberGIS? Or, and increasingly, I think, for a world in which today's hot new tools, and I'm sure there are hot new tools that are going to be talked about in the next couple of days, today's hot new tools are simply tomorrow's cyber junk. Think back 5 years and think about what tools you were excited about 5 years ago, and what are they now? So this is a very dynamic world, and it's a very difficult world, I suggest, therefore, to teach about. What exactly is a course in CyberGIS? And underlying this, I'd suggest, is the fundamental question, can education keep up? And should it keep up? Higher education is recognized to be the second most conservative industry known to humanity. Right? And I'll fill in the blank. The most conservative is classical Chinese opera. Curriculum advance is slow, and perhaps for good reason. Right? By making it slow, we do conserve what is most important. So there is a test of time involved in curriculum development. But what should our approach be here? So here's Elements of Vision Part 5. The curriculum needs constant revision, certainly in a field advancing as rapidly as GIS or CyberGIS. Textbooks are on a 3 to 4 year cycle. Typically, new editions come out every 3 to 4 years. Courses, I think most of us revise our courses every year. So let's say courses are on a 1 year cycle. The body of knowledge, what should its revision cycle be? And how frequently should it adapt to new knowledge? So, and what mechanisms will ensure a continuously evolving curriculum? What horse should we back in trying to keep CyberGIS in the curriculum? Should it be textbooks? Should it be teaching materials? Should it be online resources? Should it be massive online open courses? What should the appropriate mechanism be? What's the most appropriate mechanism for developing a curriculum in a rapidly evolving field? So, concluding points, we suggest the following. The vision of CyberGIS has advanced since the original proposal and needs to advance continuously. If we have spent the last 3 years going back to the original proposal, reiterating what we plan to do, now is the time to move forward and to think where we need to go in the future. We need to think about the next phase, whether we're talking the last 2 years or whether we're talking beyond year 6. And many other related activities are underway. We are not alone. Right? Our industrial partners are doing all sorts of interesting things in this space. The open source community is doing all sorts of interesting things in this space. To what extent are we part of a bigger movement, and what should our relationship with that bigger movement be? And I think one thing that will remain true for a while at least is that the high-performance computing community will continue to look at us as a likely domain for application and interest. So on that score, I think we have little to worry about. We will continue to have interesting relationships with NCSA and various other groups within the high-performance computing community. So let me just leave you with this. This is something that I'm sure many of you have already seen, but this is a report which was produced by the CCC, the Computing Community Consortium, which is a group partly funded by NSF to listen to the community and its ideas about the future of computing. And this particular report is based on the concept of spatial computing, which is a term designed to gather elements of computer science which are related to the geospatial case, and more broadly, the spatial case. The report came out a couple of months ago. It's online. There's the URL. And my question is, and I think it would be wonderful if all of us could consider this question to some degree in the next couple of days, what is the intersection between this report and CyberGIS? In other words, what is the intersection between CyberGIS and the computing science community's vision of the future of spatial computing? And you will find, if you do a quick search through the PDF, that the word CyberGIS does not occur in the report. Cyber infrastructure does, but CyberGIS specifically does not. So that, I would think, if all goes well with this, the intention is that this will influence NSF and its future programming. So if that intention works out, we should be part of that. And I've already had conversations with Shashi Shekhar and others about participating in meetings at NSF targeted on particular individuals at NSF. So here is somebody else's and a broader community's view of the future, and I think we need to think seriously about our relationship to it. So let me just leave you with that thought, and thank you for your attention.
It's up there.